today we're doing the second part of 21.1 probability and set theory, and we're going to go into a little bit more detail here and kind of finish up this section. There's a lot of new information, so I broke it up into two chunks. The first, we've kind of hinted at this sort of stuff already, but it has to do with the probability of any given event and the probability of the complement. Remember back when we were rolling a dice, if you roll a dice, the odds of getting, say, a 1 would be 1 out of 6, right? We could ask the complement, which is essentially what are the odds of not getting a 1? A lot of you guys would just say, oh, that's easy, that's 5 out of 6, right? So any probability of a given event plus the probability of its complement means that you've covered everything within event A, everything that's not in event A, right? So that includes all possible sample space. So in this case, it's 6 over 6 or equal to 1, right? So that's where we get this. The probability of any event A plus the probability of the complement is going to equal 1 because there's nothing that doesn't fit in between those two. We can rearrange these a little bit. We can subtract the complement from both sides, and that gives us this equation. If we subtract the event A, the probability of event A from both sides, it gives us this equation. But two sides of the same coin, basically, they add up to 1. And you just have to be able to manipulate the whichever situation is most relevant. So we're going to do this example. This one says, use the complement to calculate the indicated probabilities. You roll a blue number and a white number cube at the same time. What is the probability that you do not roll doubles? Well, this one's already kind of worded in the negative. So we're going to define event A as rolling doubles. A we're going to define as rolling doubles. Therefore, the complement of A is not rolling doubles. Oh, I guess the book does it the other way. Sorry, I would do it the other way. Ignore me. I guess event A is not rolling doubles. The complement of A is you do roll doubles, which is a little weird to me, but that's fine. So one way they suggest setting these sorts of questions up is to make a table, right? If you have two possible things, and we need to kind of figure out all combinations of those two things, we can just make this table. So up at the top we have a blue dice, at the left we have a white dice, right? If we roll a 1 on the white dice, we could also roll a 1 with a blue dice, or you could roll a 1 and a 2, or a 1 and a 3, or a 1 and a 4, or a 1 and a 5, or a 1 and a 6. You could also roll a 2 or a 1 or a 2 or 2, on and on. So the number of doubles you could get are 6, right? There's 6 possible doubles. There's 1s, 2s, 3s, 4s, 5s, and 6s, right? So they're defining that as the complement. So the probability of rolling a complement are the number of elements in that complement, right? We decided is 6, over the number of elements in the entire sample space, or the universal set. So how many elements are in here? Well, it's a 6 by 6 grid, right? So that's 36. So the probability of the complement, or the probability of rolling doubles, is 1 out of 16. And then simply we're going to calculate the probability of event A, and that equation is 1 minus 16, which gives us 5 out of 16. Obviously we could, if we needed to, add up all of these. We'd do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times 2 divided by 6. Does that work? Maybe. Gives us 30 out of 36. It's 15, yeah, so it's 15 times 2 divided by 36. 15 times 2 is 30. 30 over 36 reduces to 5 over 16. So it's much easier, as I've just proven, that it's much, much easier to just subtract this 1/6 value, right, the complement off from 1, to get the probability of event A. So there'll be other examples where it's clearly easier to use the complement. Here's another example. One pile of cards contains numbers 2 through 6 in red hearts. A second pile of cards contains numbers 4 through 8 in black spades. Each pile of cards has been randomly shuffled. If one, so they're separate piles. if one card from each pile is chosen at the same time, what is the probability the sum will be less than 12? So this is very similar than to the dice one. But we need to, here we care about the sums, right? We don't care about if they're doubles or not. So we're going to let A be the event that the sum is less than 12. So the complement will be the event that it's not less than 12, or in this case, 12 or greater, right? Again, they're going to make this little diagram. We can put the red cards over here at the top, the black cards over here on the left. There's 5 of each, right? So 2, 3, 4, 5, 6, 4, 5, 6, 7, 8. And then simply we can find the values of each one of these. So this is a 2 and a 4, so that's a 6 total. This is a 3 and a 4, so that's 7 total. Some of these, right, are going to total 12 or greater. And we can find out which ones those are, right? It's these ones here. These guys here are outcomes that total greater than 12, right? So how many total greater than 12? Well, that's 6. Weird 6. And so there's 6 elements that total greater than 12. So we can say it's 6 out of 24 is the probability of the complement of A, right? Then we can figure out the probability of A pretty easily, right, without having to count all the rest. It's much easier to do, what is 1 minus 6 over 25 than it is to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19? Let's see if that's right. 1 minus 6 over 25 is equal to 25 over 25, right? 25 minus 6 is 19. So that gives us our 19. Cool. Go ahead and try these two, see if you can figure these ones out. So pause here. Okay, so for this bag of marbles, containing 2 red, 1 yellow, 1 green, 1 blue marble, another bag contains 1 marble of each of the same 4 colors. 1 marble from each bag is chosen at random. So what's the probability of selecting 2 different colors? Well, it could be red here, and then in the other bag you could have a yellow, or a red and a green, or a red and a blue, right? So that's 1, 2, 3, 4, 5, 6. 6 there. You could get the other red, right? You could add them all up, right? It's much more difficult to add them all up. It's much easier to do 2 of the same color, right? What are the odds of picking 2 of the same color? Well, I choose 1 of the red here, right? And then I could choose 1 of the red of the other side. So that's, I'll list them all out here. So there's red, red, right? There's another red, red. So that's red 1, red 1, not sure. There's red 1, red 2, right? This is the first red. There's red 2, red 1, red 2, red 2, right? These are all 4 combinations. And then same deal with yellow. There's yellow 1, there's only 1 yellow. There's green, green, and blue, blue. Right? So how many elements are in this? There's 1, 2, 3, 4, 5, 6, 7. So there's 7 elements in this probability, right? How many possible combinations can you do? Well, there's 1, 2, 3, 4, 5. 5 times 5 is 25, so it should be 7 out of 25. Wait, why did I get 5? How did I mess this up? Red 1, red. Oh yeah. Okay, so the second bag, sorry. Another bag contains 1 marble of each of the 4 same colors. Okay, I misread that. I thought that one had 2 red as well. So that scratches off 2 of my red ones. So that's 1, 2, 3, 4, 5. 5 out of this bag has 5 things. The other bag has 4 things. So 5 times 4 is 20. So it's 5 out of 20. That's where we get that fraction. So the probability of event A is the opposite of the complement, right? So 1 minus the complement. In this case, it's 3 out of 4. Okay, the probability of not selecting a yellow marble. Again, it's much easier to calculate what is the probability of selecting a yellow marble, right? The probability of selecting a yellow marble for the first one, right, is there's 1, 2, 3, 4, 5. It's 1 out of 5 for the first. Another bag contains 1 marble of each of the same 4 colors. We'll list off the elements. That's easier. So we'll lift off the yellow one. The first one can be, if the first one's yellow, then you could have yellow, red. You could have yellow, yellow. You could have yellow, green, and you could have yellow, blue. So we'd be. You could also draw yellow out of the second one. So that means you could have red, yellow. You could have yellow, yellow, but we've already had that. You could have green, yellow. Sorry, other red, yellow. Red 2, yellow. We could have green, yellow, and blue, yellow. So that's 1, 2, 3, 4, 5, 6, 7, 8 elements out of the same sample space. So 8 out of 20. 8 out of 20. And therefore the complement is simply 1 minus 2/5 or 3/5. Okay, so those were pretty tricky problems. Again, just list off all possible elements in the set and then figure out all the elements in the sample space. And once you have those two things, you should be pretty good on the probability. The last little bit here is I just want to touch on a little mini lesson on factorials. You probably have seen factorials before, but I think it's pertinent to just kind of go over them again because it's useful. So if you haven't seen a factorial before, this is an exclamation point, and it basically is a function that says you take this integer value and you multiply it by each value that's less than it. So in this case, when we stop before we get to 0. So in this case, 1 is equal to 1, right? 2 is equal to 2 times 1, which in that case equals 2, right? 3 is equal to 3 times 2 times 1. So the timesing by 1 doesn't do anything. We can just ignore that one. So this is essentially 3 times 2, which is equal to 6. 4 factorial is equal to 4 times 3 times 2 times 1. So this is 1, 2, 3, 4, 5, 6 times 4 is 24. And then finally 5 factorial is equal to 5 times 4 times 3 times 2 times 1. These numbers get big really quickly, right? So this is the same as 24 times 5, or 120, what is that, minus 5, 120? Yeah. Okay, we need to also know how to manipulate these a little bit. So in this case, we can look at what is 5 factorial divided by 4 factorial? Well, you could write out the whole thing and calculate, what 5 factorial is, but there's a bit of a shortcut here. Remember how 5 factorial is 5 times 4 times 3 times 2 times 1? And 4 factorial is 4 times 3 times 2 times 1. Do you see anything we can cancel? Well, yeah, we can cancel the 4s, we can cancel the 3s, we can cancel the 2s, the 1s don't matter anyway. So we're left with, right, this whole thing is just equal to 5, right? The 4 factorial is basically 4 factorial times 5 equals 5 factorial, right? Because 5 factorial is 5 times 4 times 3 times 2 times 1. And this is 5 times 4 times 3 times 2 times 1. So keep these sorts of relationships in mind. So that brings us to this guy, 5 factorial divided by 5. We're essentially solving for 4 factorial here. This is 5 times 4 times 3 times 2 times 1, right? Divide the whole thing by 5. The only thing that cancels here is the 5. And we're left with this thing, which is much easier to write out as 4 factorial. Okay, so just you'll need to know how to handle factorials. Keep that in mind. Anyway, have a good one. Thanks. Bye.